Alright, so welcome to Math 21499 Research. What we're going to talk about for this one, Lecture 3, is some results in the theory of L functions and random matrix theory. And in the next lecture, we'll go into random matrix theory in a lot more detail. So, I don't know how much number theory you know, but the big thing we like to study is primes. Your primes are the building blocks. If you look at numbers multiplicatively, everything is built up from primes. How do we understand primes? There's a beautiful function called the Riemann zeta function, which encodes a lot of information about the primes. And we want to try to extract information from the primes. One of the most powerful techniques to do this is complex analysis. You can attack a lot of these problems elementarily. Elementarily does not mean it's easy. It essentially means no complex analysis. And it's often frequently harder to attack a lot of these problems. And then we love to generalize. And just like you can use the Riemann zeta function to understand primes, you can use more general L functions to understand other objects. I am not going to go into great detail on everything we're looking at. I want to just do enough so you have a sense of what the projects look like. All right, so the introduction. So why would you want to study zeros of L functions? So the first one is the Riemann zeta function. There are generalizations. You may notice I have not defined what an L function is. One of the things you learn to do in life is to either know, oh yeah, and I'll look that up at home and just be prepared for the next lecture, or if it's something that you really don't understand and need to know now, then you just ask a question. But these are just some objects in number theory. Why do we want to study them? What do their zeros tell us? Well, if you think about a classical polynomial, if you have a finite degree polynomial and you know all of its zeros, do you know the polynomial perfectly? Excellent. You know the polynomial up to a constant multiple. If it only has zeros at 1 and 3, then the polynomial is some constant times x minus 1, x minus 3. So if you know things about the roots, you know a lot about the polynomial. Then you can try going the other way. Well, what if I expand out the polynomial and I give you the coefficients? Can I get from the coefficients to the roots? And if the polynomial is of degree 4 or less, there's explicit formulas. If it's degree 5 or higher, there's no general formula that allows you to do this. So here are a couple of things that knowing zeros allows you to do. It allows you to prove things about there are infinitely many primes, and there are infinitely many primes in arithmetic progressions. It allows you to prove things about biases, that there tend to be more primes congruent to 3 mod 4 than 1 mod 4. If you know things about elliptic curves, there's more and more stuff you can do. And what I really want to just have you get out of this next slide is that, not surprisingly, the more you know about the zeros, the more you can say about a variety of problems. So the first one, zeta of s is the Riemann zeta function. All we need to know for the prime number theorem, that the number of primes up to x is about x over log x, is that this Riemann zeta function is non-zero when the real part of s equals 1. And that's enough to really understand the number of primes up to x, or more generally, Dirichlet L functions would give us arithmetic progressions. Now, if we want to understand how much is the error, the main term is x over log x. Well, how far from x over log x can you be? The main term is just on the line real part of s equals 1. The error term is the location of zeros. And the Riemann hypothesis is that all of the non-trivial zeros have real part 1/2. And that will give you the lower order term. The higher the real part of the zeros, the higher the error can be. And then the next one, the grand simplicity hypothesis, is this is what you need if you want to do more delicate things, such as this bias of primes 3 mod 4 to 1 mod 4. So in linear algebra, you talk about independence. You can talk about a set of numbers. Is the set of numbers independent over the rationals? And so if I give you the square root of 2 and the square root of 3, there's no linear combination of root 2 and root 3 with rationals that will be 0 unless you multiply both of them by 0. So we would say root 2 and root 3 are independent over the rationals. The grand simplicity hypothesis basically says, assume the Riemann hypothesis, look at all the zeros on the critical line, they're independent over the rationals, because how could they not be? And if you assume something like that, you can then prove wonderful results about these biases. And these results essentially tell you that something flows uniformly on some high-dimensional torus. All right, so the goals is to determine the correct scale to study a variety of things. I want you to see that you have very similar behavior in lots of different systems. So we're going to do number theory now. We'll move to random matrix theory shortly afterwards. I'll talk a little bit about the tools and techniques that we need to prove these results. And then, depending on interest, I'm happy to go through some of the details in a special case, or I'm happy to just say, I've got the paper written up, I probably have a lecture that's even online, and just leave it at that, because it's much easier to be at the board speaking than it is to be sitting in the audience listening. And there's a danger of information overload. So the general formulation is if you're studying some system, you observe values at T1, T2, T3. What rules govern the spacings between the events? And there are a lot of different events you can look at. You can look at the energy levels of heavy nuclei. And this is one of my favorite subjects. Is, how do you understand energy levels of heavy nuclei? How do you understand subatomic things? The best quote I've ever heard was, imagine you want to understand how a grandfather clock works. And can everybody picture a grandfather clock? What we're going to do is we're going to take two grandfather clocks, and we're going to accelerate each one of them to 0.999 times the speed of light. Then we're going to smash them into each other, and look at all the stuff that flies out, and from that deduce how a grandfather clock works. Sadly, this is how a lot of subatomic physics works. And there are analogs of all of that in number theory. There is an analog to this smashing motion. And I will hopefully talk a little bit about that. You can talk about the energy levels of matrices. The eigenvalues of matrices. And it turns out the distribution of eigenvalues of matrices does a great job modeling both nuclear physics as well as zeros of L functions. And this was an exciting connection that was first discovered in the 1970s. Hugh Montgomery was a graduate student at the time. He was visiting the Institute for Advanced Study, and he was talking to the great mathematical physicist Freeman Dyson, who wanted to know, well, what are you looking at? And Dyson said, I'm looking at the pair correlation of zeros of the Riemann zeta function, and I see the following. And then he goes, that's amazing. We see the same thing when we look at nuclear matrix energy levels of heavy nuclei. Lying ever so slightly, but that's roughly what was going on. And it was a remarkable correspondence. And so you can calculate things in two different ways, for matrix ensembles and for families of L functions. And we believe conjecturally that the main terms should match. All right. So there's often three key steps. The first is to determine the correct scale to study. The second is to have an explicit formula relating what you want to study to what you can study. And then the last is we actually need an averaging formula for the thing that we can study. So for instance, if I look at families of random matrices, I will choose maybe the matrix elements at random. And I want to understand the eigenvalues. Has everybody here done eigenvalues? Okay. Everybody know how to compute an eigenvalue? If you're thinking determinant of A minus lambda I, that is only good for theory. If you use determinant of A minus lambda I for a large matrix, it would be a nightmare. Try thinking of writing down a 10,000 by 10,000 matrix, calculating the characteristic pole. Oh, no. And it's a real issue of numerical stability. But theoretically, we can say, yeah, look at the determinant of A minus lambda I. If I want to understand the eigenvalues, I might be able to relate the eigenvalues to things about the matrix elements. And then maybe I can pass knowledge from the matrix elements on. And we'll see something very similar when we look at the zeta function and L functions in general and number theory. All right, so classical random matrix theory. So maybe we'll just do this as a joint, long lecture on both subjects. So we'll do number theory and random matrix theory together. So I'll switch to. Whoa, that looks a little bit off. Let's try that again. I think yeah, no idea. Okay, so we'll switch to classical random matrix theory. So in classical mechanics, imagine you have a universe where the only force is gravity. And you have one object. It is a pretty boring universe. So we'll make the universe a little bit more interesting. There are two objects, and again, the only force is gravity. Not bad. Now go up to three objects. And if the 3-point masses are in general configuration, we can't write down in closed form what happens. Well, if we can't even do three, what happens when we get to heavy nuclei like uranium? We have over 200 protons and neutrons and a far worse force than gravity. So Wigner's great insight was to use random matrix theory to study this. Now, experimentally, you can try to approximate the energy levels. And the idea is you would shoot neutrons into the nucleus and see what comes out. So very similar to our grandfather clock story from earlier. So this is the fundamental equation from quantum mechanics. H is your matrix, Cn is your energy eigenstates, and En are your energy eigenvalues. Has everybody here done linear algebra? Right. There are only two things that prevent this from being in the linear algebra class you've taken. The first is the matrix H is infinite by infinite, and you've probably only looked at finite by finite matrices. And the second is we don't know any of its entries. Other than that, you could, I see some people a little bit concerned, other than those two little issues, you could have studied this in your classes. So, not surprisingly, it's a little bit of a challenge to diagonalize an infinite by infinite matrix where you don't know any of the entries. So Vigner's great insight was basically, screw this. Let me look at a large n by n matrix, let me choose the entries at random, and let me calculate the eigenvalues. And then I'll do this for another and another and another, and I'll average things out. And I hope that the system average is a good approximation for what's going on for the individual matrix. So more formally, if you go back to statistical mechanics, let's simplify life and say all objects move either left or right, and we'll have everything move at a constant speed. If you want to calculate a macroscopic property like pressure, you want to know how many molecules are hitting the wall at a given moment in time, or in a small interval of time. Now, if I look at this room, is it possible for all the air molecules to be in one half of the room? Is it possible? Yes. Now, it would look very bad if on the second day of the semester or the class that I already have lost a good chunk of the students. How concerned do you think I am about this? Do you think I have emergency plans?
No.
So you don't think I'm able to rush air molecules to you if needed? You don't think I've spent any time worrying about this issue?
No, because it's so unlikely.
It's so unlikely. If you assume each molecule has a 50-50 chance of being in the front or the back, anybody have any rough idea of how many air molecules there are in the room? Within 5 orders of magnitude. So do you remember some chemistry? Anybody remember a mole, Avogadro's number? It's about 10 to the 23. There's at least a mole of air in this room. So if you guess, 10 to the 26, 10 to the 27, you will easily be within 5 orders of magnitude. Let's just say there's at least 10 to the 20 particles. Each particle has a 50-50 chance. So the central limit theorem, one of the key results in probability, says that in a lot of processes like this, the fluctuations are at the level of the square root of the number of events, or the number of possibilities. So if we have 10 to the 20 objects, I would expect 1/2 10 to the 20 to be in my half, and 1/2 10 to the 20 in your half. And I would expect fluctuations of size 10 to the 20, and then take the square root of that, which is around 10 to the 10. So I know several of you have already heard this example many times. When you talk about numbers, a number is not large or small by itself, but only relative to other numbers. Is $10,000 a lot of money? If I were to give you $10,000 now, would you be happy? Yes. If I then said, oh, I made an error, I meant to give you a little bit less, I have to take back $9,999.99. All right, you're now getting on the order of a penny. It's not that much. If you are Bill Gates, and all of a sudden you tell Bill Gates, we made an accounting error, you have $10,000 less than you thought. It's not worth his time for that conversation to happen, if it's during your work days. So it's always relative to what you're studying. Is 10 to the 10 a big number? Not relative to 10 to the 20. And so if you look at the fraction that your errors are, we expect 1/2 10 to the 20, plus or minus something of size 10 to the 10, divided by 10 to the 20. Well, the 10 to the 10 is so small when divided by 10 to the 20, it's not really noticeable. That's why I'm not really worried about you guys suffocating. If I start to see it happening, I will of course act. This is why there's some air left in this bottle. It's not just water. I can rush it to you quickly. But I'm not that worried. So we average over all configurations. Most configurations will be close to the system average. This does not mean every configuration. I could have all the air molecules on my side, or almost all. But it's so unlikely for that to happen that its contribution will be small. And then in nuclear physics, classically they chose matrices at random, they calculated eigenvalues, and then they averaged over families of matrices, usually real symmetric or complex summation. The number theorists now like to use what's called Haar measure, where there's a nice natural way of choosing a matrix at random using some group theory and analysis. We will mostly concentrate on the classical physics stuff. So a little bit more formally, here is my matrix. If it's real symmetric, Aij equals Aji. The probability that I choose the matrix A is just the product of the probabilities of each entry. Or if you want a little bit more expansion, the probability that I choose the matrix A where the ijth entry is in the interval alpha ij to beta ij is just the product of all the independent choices, and I just integrate my probability density between alpha ij and beta ij. So we say something is a probability distribution if it's non-negative, if it integrates to 1, and then the probability I take on a value between alpha and beta is just the area under the curve from alpha to beta. All right. How many of you have seen the Dirac delta function or functional? So this is essentially putting a point mass at x naught. So if you want to think about what the density is 0, spikes up to plus infinity, and then is 0 again. It's essentially the density you would get if you had a point particle. And we define it so that if you integrate any function against it, it just returns the value of the function at that special point x naught. So we might often do things at 0, but this allows us to shift things a little bit. If you don't like functions like this, which is quite okay not to like them, because they're not really functions, what you could do is you could do approximations. You could take a very, very thin Gaussian. And a very thin Gaussian would almost be the same as this. And you could take the limit as the width of the Gaussian shrinks. And you would essentially recover all of this. So to each matrix A, we attach a probability measure as follows. I have n eigenvalues, so I'm going to put a point mass at the eigenvalues divided by 2 root n. And because I have n eigenvalues, I divide by n, or put a massive size 1 over n at each one of them. So when you look at this, there are two things that should come to the forefront. There's a 2 and there's a square root of n. Which do you think is the more important, the 2 or the square root of n? The square root of n. This is what's going to be changing as n changes. The 2 is so I can say semicircle rather than semi-ellipse later. It's the n that really controls the behavior. And it's going to give me something that has a chance of converging to something independent of n as n gets large. So if I integrate from a to b of my density function, it's going to count how many normalized eigenvalues live between a and b. And if I want to calculate the kth moment, I would integrate x to the k times this, and I would just get the following. So the idea is if I give you a nice function, if I want to understand a probability distribution, if I understand the moments, hopefully I understand the distribution. This is false. It is possible to have two different probability distributions that have the same sequence of integer moments. There's a beautiful paper, Can You Hear the Shape of a Drum? If you know the different vibrations, frequencies that the drum can go in, is that enough to figure out the shape? And the answer is, I believe, no. You have similar issues here. But if you put on some additional conditions, it is enough. Has anybody here taken complex analysis? Okay. If you take complex analysis, if you know that they have the same moments, not just at integer values, but at a sequence of values that accumulate to a common value, say, at 5 plus, maybe 6 minus a half, 6 minus 2/3, 6 minus 3/4, 6 minus 4/5, something that's converging down to 5. If you know you have agreement along a sequence of moments that converges, then that is enough to give you uniqueness. We won't worry about that. We'll just use, by abstract nonsense, if we know the moments, we can then prove that this means it converges to something nice. And this is going to be our tool for understanding things. So it turns out that if you choose your matrix, real symmetric, choose the matrix elements independent, identically distributed, mean 0, variance 1, and other moments finite, this is basically just to normalize. If my distribution is nice, I might as well center things so that everything is mean 0. I might as well choose my units so that it has variance 1. And then with probability 1, almost all matrices have their density of eigenvalues converging to a semicircle. And let me give you a sense of how you attack a problem like this. So how many of you remember the eigenvalue trace lemma from linear algebra? the sum of the diagonal elements of the matrix is equal to the sum of the eigenvalues. Did you ever have any application of this result when you did linear algebra? Or was it just like theorists being theorists? We can prove this, so let's prove this. This is one of the most useful results in all of linear algebra. And the reason is the following. We understand the matrix elements of A. We're choosing our matrix by choosing the elements at random. We want to understand the eigenvalues. Well, this relates the sum of the eigenvalues to the sum of the matrix elements. And so the idea is, if we can understand the sum of the matrix elements, hopefully we can pass that to sum of the eigenvalues. Now, if you think about what's going on, this is essentially the kth moment of the eigenvalue distribution. Just put a factor of 1 over n. If I normalize things, fine. I got some 2's and root n's as well. I don't care. This is essentially the kth moment. If I know all the moments, I should know the distribution. And so the hope is that by understanding these traces, we can then use that to understand these moments. And if we can understand the moments, we can understand the distribution. We would love to work with the eigenvalues, and we have knowledge about these. So this is a nice polynomial. There's a chance of being able to evaluate this. Next thing, how many of you have not seen the central limit theorem? All right, everybody has either seen it or can have a good enough straight face, and then just look it up later. Excellent. All right, so let's look at the trace of A squared. It's the sum of the squares of the eigenvalues. By the central limit theorem, well, the trace of A squared is the sum of Aij, Hij. Each one of these is mean 0, variance 1. It's real symmetric, so these are the same. So this is Aij squared. So each of these is on average 1. So the sum should be of size n squared, and fluctuation should be much smaller. Okay. So this is of size n squared. So the sum of the squares of the eigenvalues is of size n squared. We have n eigenvalues. So this tells you each eigenvalue is roughly of size square root of n. So when we go to the formula we had from several slides ago, when we had this 2 root n, we can now see where that root n is coming from. It's coming from the central limit theorem telling us that on average, the eigenvalues look like square root of n. There is a bit of a lie here. I have n times the average is n squared, so I'm saying that the average, but this is an average with squares, and this is an average without. This is meant to be a little bit of a heuristic and just give you a sense of what is the correct scale. You can then go through, and now that we have this insight to use square root of n, do the calculation and see that it does work out, and that this is the right way to look at things. There is nothing wrong with doing heuristics to get a sense of what you should be looking at, to get a sense of what the answer should be, and then trying to prove things very carefully. There is a little bit of an issue because I'm dropping the square. But we're getting the average of the squares is of size n. So if the average of the squares is of size n, yeah, it seems reasonable that the average of the individual ones should be of size root n. All right. So now the kth moment is just the trace of a to the k divided by some gum, involving 2's and n's. So the average kth moment is we take the kth moment of a fixed matrix and we weigh it by the probability we chose that matrix. And now all we have to do is evaluate this integral. So this is an integral involving a polynomial of the matrix elements times our measure. So this is going to be multivariable calculus of the Wazoo. All right. So we calculate the moments, and we calculate what the kth moment is on average. You would like to then say that if you know that the average kth moments converge to the moments of the semicircle, then the distribution converges to a semicircle. You need a little bit more. It's not enough that the average is correct. You need to show that the variance is going to 0, so that things are strongly concentrated. If I tell you on average, everybody has $100, well, maybe half the class has 0 and half the class has 200, and then nobody is near the average. So you want to be able to show that almost every matrix is close to the average. It's not enough to just compute the averages. But it turns out that the same method that calculates the average also allows you to calculate the variance. So it's not a big deal at all. All right, so let's see how to calculate these things. I am deliberately going to do a ridiculously easy example. It is very misleading as to how hard the problems are. Let's calculate the second moment. So we'd have to calculate the double sum aij. I don't know why I wrote ji. Because it's a finite sum, I can switch the order of the sum in the integral. And now when I look at this, well, when I have, let's say ij is 3, 5, then I would have the 3, 5 p's, the probability of A35, dA35, and then I would have everything else, every choice of KL that's not ij. Because these are probability distributions, these all integrate to 1. Because it's mean 0, variance 1, this is actually the same as the calculation of the variance, so this is also 1. So this whole integral is 1, so I just get 1/4. And then you just do that for higher moments. And then the hand's going like this hides just how bad it is for the higher moments. And I want to talk a little bit about that because that's where we're going to be able to draw a lot of very interesting questions. So for the higher moments, we now have an expansion like this. We're assuming our random variables have mean 0. If any of these aij's is unmatched and it's just floating by itself, then the integral will be 0. So everything has to be matched in at least pairs. And then you can start to ask questions, could I have a triple match? Could I have 2 triple matches? Or it turns out if you have even 1 triple match, it's going to be a lower order term. You look at the power of n you're dividing by, and if you have even 1 triple match, you just count on your fingers, and you see that it's not going to contribute. So you have everything matched in pairs, then you have to say, well, which pair matchings will contribute? Maybe I match the first with the second, the third with the fourth, or the first with the fourth, the second with the third. Do all of those contribute equally? And so now you can see the combinatorics emerging. And interestingly, if I give you 2m numbers and ask you how many ways can you match 2m numbers in pairs, the answer is 2m minus 1 double factorial. Has anybody seen the double factorial? What is the double factorial? So what would 7 double factorial be? Yes?
Is that what you're taking out, so it's 7 times 5?
Yes. So it's not the factorial of the factorial. So the reason it's not the factorial of the factorial is because that doesn't really arise in many probability problems that we care about. Thank God. Okay, because the factorial of the factorial is just going to be monstrously large. So this is just every other. So this is 7 times 5 times 3 times 1. Okay? And if I gave you 6 double factorial, it would be 6 times 4 times 2. It's every other. And so we have 2m minus 1 double factorial. And that's going to be the number of ways we can match things in pairs. Interestingly, this is also the 2mth moment of the standard normal. So there's a lot of really interesting connections with probability. As a nice exercise, prove that the number of ways to match 2m objects in pairs is 2m minus 1 double factorial. So if I match things in pairs, maybe I matched with Joshua, you two are matched, you two are matched, you two are matched, and we had to kill you, sorry. Or you get matched with the water bottle that's here to save us if we're running low on air. Or I could match with you, and then you two could match. But matching me with Joshua is the same as matching Joshua with me, and it doesn't matter if we call ourselves the first pair or the last pair. All that matters is who's matched with whom. So it's a nice exercise. Prove that that's 2m minus 1 double factorial, and prove that that is the 2mth moment of the Gaussian. Right. So it becomes more involved when you consider other moments, as k gets larger and larger. So some numerics. Here's 500 matrices drawn from a 400 by 400 Gaussian. The red line is the semicircle. You can see it's a pretty good fit. Have any of you seen the Cauchy distribution? So Cauchy, P of x is 1 over pi when divided by 1 plus x squared. What's nice about this distribution is this distribution has infinite variance. You can get into arguments as to whether or not it has mean 0 or not. The improper integral does not exist, but it clearly has infinite variance because if you try to integrate x squared over 1 plus x squared goes to 1. The Cauchy distribution does not have finite variance. And for the Wigner semicircle law, we need finite variance. Do you think, however, that maybe that was just a proof of convenience? Do you think Wigner's law will still hold if we put in the Cauchy? Or do you think we actually need that? All right, let's see. This is what you get if you use the Cauchy distribution. All right. Very different. It does not spike up over here. This is just counting how much of the probability was this large or larger. Very, very different behavior. The density of states does depend crucially on the on the variance being finite and the higher moments being finite. When you look at these expansions, and I said, well, if you had a triple, it doesn't matter. Well, these things start to matter if you have higher moments that are going off to infinity. All right. So this was a conjecture when I was young. It's now a theorem that if you look at the spacing between normalized eigenvalues, that you get a universal result. And at first it was only known if you chose your distribution from a Gaussian. It's now known in general. And it's approximately the following shape. And so here is the uniform distribution on -1, 1. And you can see it's pretty good agreement between theory and conjecture. Okay. I'm looking at 5,300 by 300 matrices. What do you think will happen if I use the Cauchy distribution? Well, what do you think about the fit? Much worse. Why do you think it's so much worse? So here's the uniform. Here's the Cauchy. Any thoughts? So this is one of my favorite XKCD strips. Guy goes to the woman, I think we should give our relationship another shot. We should break up and I can prove it. Huh. Maybe you're right. I knew data would convince you. No. I just think I can do better than someone who doesn't label her axes. What's the difference between these two cases?
The scale.
What do you mean by the scale? I'm sorry?
Are you using 300 by 300?
Yeah, I'm using 300 by 300 for the uniform, and I'm only using 100 by 100 for the Cauchy. What if there's a convergence rate? What if you don't get to the limiting value immediately? To me, I love examples that can really highlight what's going on. And these are chances to just really drive home points for the rest of your life. I will do the following. So I'll kill all this. Okay. Can someone tell me what 16 over 64 is in lowest terms? 1/4. Not so hard. 19 over 95. Maybe a little harder. What would that equal? 1/5. All right, let's do 2 more. Let's do 49 over 98. What would that be? 1/2. Okay. And let's do one last one. Let's do 12 over 24. I'm sorry? 1/4. Right? Am I the only one who gets 1/4? All right, 16 over 64, I cancel the 6's and I get 1/4. 19 over 95, I cancel the 9's and I get 1/5. 49 over 98, I cancel the 9's and I get 4/8, which reduces to 1/2. So of course, for this one, I must cancel the 2's and get 1/4. No. Anything I can do to really drive home points so that you will remember to never make that mistake again, I want to do. I love this example. Proof by example, no. Proof by exhaustion, yes. If you enumerate every possible case, that's fine. But just because we've checked something 3 times, we might begin to get some comfort, some confidence in what the answer is, but that's not the same as a proof. And it's extremely important to remember that difference. Okay. So always label your axes. If you're writing in LaTeX, if you have code that generates your pictures, comment out that code and keep it in your tech file. And if you need to change things, then you can change it later with great ease. But you always want to be looking at the labels. If I go to a 300 by 300 quotient, it's actually a pretty good fit. And what this tells you is that the spacings between normalized eigenvalues is a more fundamental question than the density of states. You can look at a lot of different things. You can look at graphs. And so I have a bunch of vertices, I have lines connecting them. You might want to put on constraints. Maybe you're not allowed to have multiple edges between 2 vertices. You can form an adjacency matrix where Aij is the number of edges from I to j. And you can ask about the distribution of eigenvalues. These are real symmetric matrices. And here is what you get when d equals 3. Does this look like a semicircle? But if you go up to d equals 6, it looks a lot more like a semicircle. And as d increases, so this is a d-regular graph, that means each vertex has exactly d neighbors. As d gets very, very large, it rapidly converges to a semicircle. And this illustrates the type of families I like to look at. I want to look at what I'm going to call fat, thin families. It's fat enough that we have averaging tools at our disposal to do the analysis. But it's thin enough so that you don't get the same universal behavior. So I am primarily a professor at Williams College, which is a liberal arts institution. It is a very different school than Carnegie Mellon. At Williams, I might ask, does anybody here know how to program? At Carnegie Mellon, I would ask, what's your 2 or 3 favorite languages to program? It's a very different environment. On average, I think the math skills at Williams among the top students are comparable to the skills of the top students here, but we don't have the same depth, and the undergraduate body is going to be very different. If I choose somebody at random at Williams, I could easily have somebody who's a humanities lover who just doesn't like science, doesn't like quantitative stuff. I might actually get somebody who does, but I'm more likely to get somebody with very different behavior. Whereas here, if I'm choosing somebody at random, I have a much better chance of still having strong math skills, even if they're not a math major. And so you want to have a family that's thin enough so that you're not just seeing the same stuff again and again. This is the spacing between adjacent eigenvalues of 3 regular graphs. And again, you see that same behavior we were seeing before, incredible universality. So what I want to do now is just talk a little bit about some general families of matrices and give you a sense of what kind of problems you can look at. So the first is real symmetric Toeplitz matrices. And all these slides I'll post online. So a Toeplitz matrix is constant along diagonals. And I got interested in these because I was working at the American Institute of Mathematics. I had several students working with me. 2 of them were from Princeton, where I had just left, and 1 was from Ohio State, where I was just going. And unfortunately, the way funding worked, I only had enough money to take the 2 Princeton students with me to a conference in Hawaii. And I had to leave the Ohio State student at the American Institute of Mathematics. He started looking at things that were Toeplitz, and then when I came back, oh, well, you're interested in Toeplitz, let's look at Toeplitz matrices, and let's see what happens. And so what's interesting about these is you have very few degrees of freedom. You essentially have n degrees of freedom. Or maybe n minus 1. You might as well assume b0 is 0, because all that does is it shifts all the eigenvalues by b0. You might as well assume it's 0. What can you say about the distribution of these highly structured matrices? Is it going to be the semicircle again, or is it going to be something new? And so again, you can associate the eigenvalue measure, you can calculate the kth moments, you can do all these things as before, you can show all the odd moments vanish, you can show the first moment is 1. When we did numerics, it looked like the behavior was a Gaussian. It looked like every matching contributed equally, and we told this to some people and they gave us heuristics as to why it should be a Gaussian. Eventually we discovered there was another group looking at it at the same time as us, and they too thought it was a Gaussian. It's not a Gaussian. And so what we can do is we can have AIJs, we'll write it as which diagonal it's on, and the B's have to be matched in pairs. So if two B's are matched, you have two possibilities. There's either a plus sign or minus sign in the matching. Whenever you see algebra like this, you basically just quickly look at this, okay, if my life depended on it, if I was interested, I could go home, I could read it carefully and follow what's going on. All he's saying is you do some calculations and some things fall out. When you do the calculations, you find that all of the signs must be, I think, minus or positive. Only one choice of sign works. All the signs must be minus. Okay? So that gives you the main moment is at most the moment of the Gaussian. If everything contributed equally, you would get the Gaussian. And so we started to look at, well, let's try to calculate the fourth moment. So things must be matched in pairs. So here's I, J, J, K, K, L, L, I. So one possibility is I can match with your neighbor, or I can match across. And by symmetry, the first and the third are identical. If I can handle one, I can handle the other. You can show that the first and the third contribute fully, and the second one with the crossing doesn't. And so in the first case, it has to be with a minus sign. You go through and you get I1 equals I3, I2 and I4 are arbitrary. So I have 3 degrees of freedom. So I essentially have n cubed triples that all work. I'm dividing by n cubed. It's going to come out perfect. In the second case, I have I1 minus I2 is minus I. So when the dust settles, I get I1 is I2 plus I4 minus I3. If I choose I2, I4, and I3 freely, there's n choices for each one of them, that's n cubed tuples. The problem is I1 might be outside the range of 1 to n. If I2 and I4 are at least 2/3 n, and I3 is at most 1/3 n, you can see that this is going to be too large. Conversely, if these are both 1/3 n, and this is at least 2/3 n, it's going to be too small. So this is enough to show that you lose a positive percent. If you do a little bit more work, you can show you actually lose 1/3 of the triples, or something like that. And so we end up getting that instead of having a fourth moment of 3, it's 2 2/3. I could have done this lecture very differently. I could have shown you this curve and asked you, does this look like a Gaussian? Or even better, doesn't this look like a Gaussian? Look at the Gaussian behavior. Now that you know what to look for, you can see, well, actually, the decay doesn't look quite right. It looks like it's decaying a little bit faster than you would for a Gaussian. And that's coming from the moments being smaller. And so we were able to prove that it converges to a unique measure that's not a Gaussian. And then we showed that if you added an additional condition, if you made the first row of the Toeplitz matrix a palindrome, so A, B, C, dot, 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 C, B, A, that fixes all of the obstructions, and you end up getting a Gaussian. So it was a nice way to bring number theory into the problem. There's a whole slew of other things you can look at. This is spacings between adjacent eigenvalues, very different than the real symmetric matrix. This is more like Poissonian behavior exponential decay than the other stuff. I'm going to do a little bit of block circular ensembles just because the math and the pictures that arise are so much fun. So this is a generalization of Toeplitz matrices. Instead of being constant along the diagonals, it's now periodic along the diagonals. And you can choose the length of the period. So I love to have like dials in my mind so I can change the structure. And here this is periodic with period 2. The Toeplitz would just be periodic with period 1. And you could ask, what happens to your matrix? And the idea is, as the period gets longer and longer and longer, what do you think the matrix is going to look like? So the period gets very, very long. What is the matrix going to look like?
Any other symmetric matrix?
Yeah, like a generic real symmetric matrix. So in the limit, as the period goes to infinity, I would expect to see the behavior of a semicircle. And as the period goes down to 1, I expect to see a Gaussian. All right. So you can go through all the stuff as before. Basically, you need to keep track of how many times you have things matched in pairs, triples, and whatnot. How many of you have taken topology?
There's actually not an undergraduate topology class here.
Okay, so all I will say is there's something called topology, and this is just to give you a sense of where it can start to emerge. You can assign orientations to the sides, and you might talk about folding things up, and if they are oriented in the same way, they align, and so this line is really the same as that one, and just folding together and seeing what shapes you would get. So if you take like a piece of paper, if I identify this side and this side with the same orientation, I now get a cylinder. If I identify this side and this side and I fold it in, I would get a hollow donut. And so you can get different shapes over here, and it turns out that the only ones that contribute are the ones that are matched in opposite orientation, which are the ones that are going to fold up nicely. And so there's now there's a connection now between the geometry of the topology and the contribution to the moments. And there's a lot of stuff that you can go through here. I'm not going to go through the details, but the stuff comes in. And at the end of the day, we actually have an explicit closed form expression for the density. And so here is the formula for the density. When you look at this, as you set it m to infinity, it does not look like this converges to a semicircle, but it does. And so here's some plots. This is a plot when m equals 1. Looks pretty Gaussian. M equals 2. You can see it actually does a pretty good job of capturing the up and down motion. And this is looking at just matrices that are 400 by 400. And I'm only choosing 100 of them. Not much data, and you can already see it. At 3, it's still able to pick up all the stuff. And you can see very quickly it's converging to a semicircle. Now, for any finite period, it is going to go off to infinity, but it's going to go off to infinity so rapidly. And the reason it's so rapid is you have this e to the negative mx squared over 2. So that's going to really cut down on the probability. And then just here's a nice plot of looking at a bunch of them all together and just seeing how rapidly it's converging to a semicircle. So for some problems, it's fascinating which math has to come into play. Now to me, what makes problems interesting is trying to find behavior that no one has seen before. It's very hard to get an explicit closed form expression, so it was exciting when we got that. So the next one is going to be called checkerboard matrices. It should be very clear as soon as you see them why they're called checkerboard matrices. And they led to some very strange behavior. So here I'm going to do a checkerboard, standard checkerboard. And let's say in either all the white squares I'm going to put a W. I'm going to put the same number in each place. So I've lost half of my possibilities. And I can ask, what is the distribution of the eigenvalues of this matrix? And it turns out that, I'll skip all this. I'll skip this. You have something that looks like the following. Most of the eigenvalues are semicircular, and there's a small number, and it's related to the length of the checkerboard. So if I do it every 2, I'll have on the order of like 2 things. If I do it every 3, I'll have 3 things. I'm averaging this over a huge number of matrices. That's why I have so many data points here. But for each matrix, there's like k eigenvalues that we call in the blip. And all the other ones are in the bulk. And it was a really challenging game to isolate the 2 parts individually and see what their behavior is. This has fascinating behavior. But the number of there's only 2 of them, and they're of size n, these are of size square root of n. These are drowning out those in some sense. In another sense, these ones drown out these. Because if you look at higher moments, if these are of size n and these are of size square root of n, if you look at n to the 5th, n to the 5th is much larger than square root of n to the 5th. Even if you only have a bounded number of eigenvalues, even if you only have 2 of these and you have n of these, n times root n to the 5th is much less than n to the 5th. So these small number of eigenvalues can actually drown out the entire bulk. And what happens as you go further and further, as n gets larger and larger, is the blip moves off to infinity. This is related to the differences in size. And so we were able to figure out how to explain what was going on and see what was happening there. And then one of the projects I want to do is related to a new way of looking at matrix ensembles. And this is inspired by some things from number theory, so I'm going to now switch back to number theory. So I think these slides should be okay. All right. So it is time to look at the Riemann zeta function. This is one of the most important functions in all of mathematics. It's defined as the sum over all integers of 1 over n to the s, and if you use the fundamental theorem of arithmetic, it turns out it's the product over all primes of 1 minus 1 over p to the s inverse, at least if the real part of s is greater than 1. All right. Can anybody give me the next integer after 2019? I'm sorry?
2020.
Yeah, that took a little bit too long. Next one after 2020.
2021.
All right, next one. Much better. There is really no mystery in the study of the distribution of the integers. What's the next prime after 2019? And the next prime after that, and the next prime after that. So the idea is we know everything about the distribution of spaces between integers. We know where the integers are located very well. We even have a formula for the nth integer. Right? We don't have formulas like this for the primes, and so the hope is that maybe by understanding this function, we can pass that knowledge to knowledge about the primes. All right, so here's a rough proof, unique factorization. Every integer can be written uniquely as a product of primes. This is why 1 is not considered a prime. Because if 1 were a prime, you would not have unique factorization. And then basically the idea is you need to just be careful about this, but if I look at the product, I use the geometric series formula to expand each term. I have 1 over 1 minus r. I expand each one out, and then I multiply. You've got to be careful because there's infinitely many things. So what you can do is you can look at only finitely many primes, and you can truncate these products, and when you expand things out, you can see you get a subset of the sum over integers. But if I wanted to have, 1 over 12 to the s, I would have 1 over 2 to the s squared, and then 1 over 3 to the s, and then that would give me 1 over 12 to the s. And each term is going to be gotten in one and only one way. So this should give you some idea of why we care about the zeta function. So if you let pi of x be the number of primes at most x, here are some connections between zeta and pi. So the first is the most common one, that if you look at the limit as s goes to 1, this becomes the harmonic series. The harmonic series diverges. Therefore, there must be infinitely many primes. And in fact, with a little bit more work, you can show from the divergence of the harmonic series that the sum of the reciprocals of the primes diverge, and you have some rough idea of how large that would be if you sum all the reciprocals of primes up to x. So the sum of the harmonic numbers, if you sum 1 over n up to x, it's about log x. You can use that to get the sum of the primes. Reciprocals up to x is about is about log x. Here's a more interesting one. Zeta of 2 is pi squared over 6. How many of you have seen this result? Okay. This proves that there are infinitely many primes. So can somebody tell me why zeta of 2 being pi squared over 6 means there are infinitely many primes?
If there are a finite number, then that would be it, and the product would be irrational.
Then this product would be rational. So there must be infinitely many primes. Now, initially, it gives you no information about the rate of growth of primes. If you look at Euclid's attack, there must be infinitely many primes. If not, enumerate them, multiply, add 1. That's either prime or divisible by new prime. That gives you a growth rate on primes. The growth rate sucks. It gives you that there's at least like log x primes up to x, but it's a growth rate. It goes off to infinity. When I was a postdoc at Brown, maybe 15 years ago, I was intrigued about this, and I was wondering if you could use this to get a growth rate on pi of x from the fact that we know how irrational zeta of 2 is. And so I was able to get, initially my first result was a growth rate that there are at least log x primes up to x. Now this is worse than Euclid, which gives log x. So I see some of you laughing. It's so nice that you're supporting my work. Thank you. But you should really hold off on your laughter until you hear the rest of the story. How do we know how irrational this is? Well, there's a series of papers that deal with something called irrationality exponents. And one of the ingredients in the irrationality exponent calculation is the prime number theorem, that there are x over log x primes up to x. So using that there are x over log x primes less than or equal to x, I am able to prove that there's at least log x primes up to x. So the result is even worse than you would expect. So I then opened this up with some of my students and said, okay, let's look at this proof on the irrationality, and let's see where do they actually use the prime number theorem, and what can we do without. And at the end, after a lot of work, we were able to go that there's at least almost x over log x primes infinitely often. So we were able to get infinitely close to the correct result infinitely often. So in the end it was nice, but the initial result was weaker than Euclid, and it was assuming more than it was trying to prove. It was, at the time, the worst result I had ever proven in my life. But it's a great story to give in a class like this, when you will have a tendency to use papers where you may not have read everything. And you want to be very careful whenever you use something if you do not understand all the lines. I know I've shared the story with some of you. I had fun with a graduate student when I was a postdoc at Ohio State. He showed me his thesis. He was very proud of what he had proved. I looked at it and I had some fun with him. I go, oh, very nice. Do you realize half your thesis is wrong? So I knew he was quoting from a paper that said, we assume k is congruent to 2 mod 4. If k is congruent to 0 mod 4, there's a trivial modification. All you had to do was split his result, and if k was 0 mod 4, you have to put in a negative 1. It was not hard to fix his thesis. There may be better ways to communicate to this fact to him rather than giving him a heart attack, but it really drove home the point of, if you are using a paper, you must be very careful about the results you are using. Sadly, a lot of authors do not explicitly state what they have assumed. And so if you are using a paper, you should read the theorem carefully, and you should read the entire paper up to that point, in case they ever say, for convenience, we always assume. All right. There's a lot more connections, but this is at least some. So the Riemann zeta function can be extended to a function that's defined for all values of s, and it has a simple pole at s equals 1. This is the gamma function. Have people seen the gamma function? It's a generalization of the factorial function. So there's just some functional equation that relates its values at s and 1 minus s. And the Riemann hypothesis is that all the non-trivial zeros have real power half. So you can write the zeros as 1/2 plus I gamma. If this is true, then the zeros are all on a line, and you can talk about spacings between adjacent zeros. It's the same as energy levels of heavy nuclei. If the Riemann hypothesis is false, if you could have zeros off the line, you can't order the zeros. You can't order the complex numbers. But this gives you some idea that maybe all that stuff we were doing in random matrix theory, maybe we can apply that here. It turns out rather than looking at the Riemann zeta function, we can look more generally at L functions. And before we had a 1, now I'll have just some numbers AF of n. We always want to have an Euler product. We always want to be able to write it as a product of local factors. We want to be able to have some kind of completed function where we put in some stuff here. And it relates the values at s to 1 minus s. So is there anybody here who has done some stuff with elliptic curves or anything like that? Okay, so I will give you a little bit of warning. Depending on which paper you read, for elliptic curves, the L function could be living in the critical strip 0 to 2 or 0 to 1. And if they tell you we're looking at s equals 1, s equals 1 could be the center of the critical strip, or it could be the edge of the critical strip. If you work in automorphic theory, you always normalize it so it's s into 1 minus s. But if you're looking at just elliptic curves, it's a little bit more natural for elliptic curves to look at from 0 to 2. So you always have to be careful at which book you're looking at. I will just state the worst notation I've ever seen in my life. Yes. So I saw this in a physics book. Anybody want to guess what this is? I'll tell you what any of the 3 letters mean. You can choose. Which one would you like to know? P is force. Can you figure out what law this is? Any guess?
I was going to guess Newton's second law.
Yeah, force equals mass times acceleration. This is the worst notation I have ever seen in my life. You really want to think about what are you choosing for your notation. You want it to be something that you can look at and understand. Yeah. Right. This is horrible, horrible notation. For elliptic curves, you've got to be careful. It is very easy a lot of times different authors will have different normalizations. You need to be aware of that. We believe the generalized Riemann hypothesis holds for all these nice functions, that they can also be written as 1/2 plus I gamma. And it seems like the spacings between heavy nuclei and the spacings between zeros of L functions and the spacings between eigenvalues matrices, they can all be described by the same type of mathematics. So let me give you a sense of the type of problems you can look at. So if I give you an elliptic curve, y squared is x cubed plus ax plus b, let's say a and b are integers, I can look at all pairs of rational numbers that solve this. So imagine p and q both have rational coordinates. And I can write a line connecting them, y equals mx plus b with rational coordinates. If I substitute that in here and expand everything out, I end up getting a cubic with 2 rational roots. And it has rational coefficients. Therefore, the third root must also be rational. So if you draw the line connecting p and q and call that r, it turns out its reflection is how we will define p plus q. And this allows you to create a abelian group on the elliptic curve. And you can ask questions. And one of the things you can ask is, well, let's form an L function. And I'm not going to go through explicitly how you would define it, but I'll choose my APs to be related to the number of solutions modulo P. So what we're doing is we're looking at local data. We're fixing a prime, and we're trying to count how many solutions are there. Well, if you think about this equation, if I fix x, half of the numbers from 1 to p are squares, and half of the numbers are not squares. And if it's a square, then there would be 2 choices for y unless the square is 0. So you might expect half the time you get 2 roots, half the time you get no roots. You might expect that there would be roughly p solutions. That's why I'm looking at p minus this, because this is basically subtracting off what we have from what we expect. And it turns out that these fluctuations of size square root of p, you can then use this to build an L function. It's going to converge. This is one of the ways we actually attack things like Fermat's last theorem through stuff like this. And the Birch-Swinnerton-Dyer conjecture says that if you go back to this group of rational solutions, it has some torsion component and it has some number of copies of z. And the number of copies of z, this infinite part, is very mysterious. This number r is called the geometric rank. One of the big open problems in mathematics is that the geometric rank is conjectured to equal the analytic rank, the order of vanishing of the L function at the central point. Way beyond what we can do, but we can do some things to show that it's a reasonable conjecture. You've seen this slide before about why we care about a lot of things. Let me show you how you can actually get your hand and attack a bunch of these problems. So we started with random matrix theory. We started by looking at a matrix where we chose the entries and we wanted to pass from that knowledge to knowledge of the eigenvalues. If I have an L function, I want to understand its zeros, but it's the coefficients of the L functions I know things about. For elliptic curves, I know things about the coefficients of the elliptic curve, the number of solutions modulo P. And I want to use that to pass things about the zeros. So you should have Pavlovian reactions to certain things in life. Okay? If you see a product, you should have a Pavlovian reaction to take the logarithm. Now, if you are teaching multiplication to 5th graders, resist. Right? That's not a good time to take logarithms. But essentially, any other time, if you see a product, you should take logarithms. And this is why it's so nice that our L functions have 2 different representations, as a series and as a product. The log of a series is painful. The log of a product is pleasant. So no one here has done complex analysis. But one of the big tools you have in complex analysis is the logarithmic derivative. You take the logarithm of your function and you take the derivative. So when you take the derivative of the log, you get 1 over zeta, zeta prime. And it's just convenient to put in a minus sign here. I clearly want to use the product expansion, not the sum expansion, because the log of a product is the sum of the logs. All right. I am not going to justify steps, so I now have the derivative of the sum. The negative 1 just came down. All right. Well, what I can do now is I can take the derivative term by term. You can justify this. And now I'll use the geometric series over here to expand out my denominator. This is the first term, and then all the other terms I'm going to put together in a function called good of s. And as the name indicates, you can handle this without too much trouble. And now, when I do some contour integration, and this is where some complex analysis is useful, you can actually learn most of the complex analysis you need in about 1 hour. Complex analysis allows you to evaluate a lot of integrals by converting them to algebra. And when you do things such as quantum integration like this, you get contributions from the zeros and the poles of the Riemann zeta function. So this stuff over here is going to be essentially information about the zeros. And now I'm left with this function over here to integrate. It turns out this is a tremendously nice integral. If p is less than x, this integral is 1. If p is greater than x, it's 0. And if p equals x, you get a half. So this integral essentially detects if your prime is at most x. And so this is essentially going to be the sum of log p up to x. In general society, is it good to discriminate? Yes or no? Right? We should not be discriminating. We should be treating people equally. In number theory, can you discriminate? Not only is the answer yes, but it's actually encouraged. But you have to be careful by how much you discriminate. Here, we have a log p weight. We are not treating all primes equally. This makes the analysis a lot easier. So how many of you have seen proofs of the prime number theorem or theorems counting how many primes there are? All right, so I see like 1 or 2 hands kind of going like this. This is why we put log p weights. So this is why we have all these functions working with logarithms. It's coming from the Riemann zeta function. There's this natural weighting attached. The weighting is not horrible. If I have something of size x and something of size x over log x over log x is much, much smaller. But when you take the log of both of them have a main term of log of x. And they differ by log x. Well, log x is much, much smaller than log x. So even though x and x over log x are significantly apart, on a log scale they're essentially the same. So this is a very slowly varying weight. This is a very small amount of discrimination, but it makes the analysis a lot easier. And a lot of Fourier analysis is going to come into play here now. And so now I can write, instead of using the function x over s, I can use a more general function phi. And instead of p to the minus s, if I write s as sigma plus it, I can write this as phi of s e to the minus sigma log p e to the minus it log p. And if you've seen the Fourier transform, this is essentially now just the Fourier transform of this piece over here. All right. So what we can now do is we can now start to calculate things about zeros of L functions. It's very similar to the random matrix theory stuff. So I don't want to go into too much detail here. If people are interested, I will give you some technical stuff to read, and there will be technical stuff that you will need to read for this. But there are sequences of papers where we can calculate sums like this. There's a lot of universal behavior. I'm going to skip this. Okay, so I'm going to go back to the other set of slides. Okay. And so I actually was trained in number theory, not by a mathematician, but by a physicist. Frank Ferk, he was actually one of the original nuclear physicists, one of the original experimenters to gather the data in the 1950s that led to Wigner then making this great conjecture about random matrix theory describing things. So here is a dictionary to pass from number theory to physics. All right. In number theory, we study zeros. In nuclear physics, we study energy levels. How do we understand the energy levels? We shoot a neutron into the nucleus and see what happens. On the number theory side, we shoot a test function. That's what we were doing right here. We shoot a test function phi. We would love to shoot an arbitrary neutron in an arbitrary energy level, but we can't do that. We can only shoot in neutrons whose energy lies in a certain band. And based on that, we then get certain information about the internal structure. It's the same thing over here in number theory. We can only evaluate the sums that arise if the Schwartz function is suitably restricted. And so there really is a nice interplay between the two. Now going into a little bit more detail, So I'm now at the point where I can now say a little bit more about number theory and then lead into the random matrix theory project, and then I'll switch to the number theory project. So again, I'm not trying to give you all the details, I'm trying to give you just enough to understand. In chemistry, you talk about compounds, right? What are compounds made of? It's been a while since I've done chemistry too. How would you make a compound in chemistry? What would you combine? Atoms. So the idea is if you understand atoms and you understand the rules of combinations, you can then hopefully understand what's going on with the compounds. You want to break things down to the constituent part. Just like for numbers, you might want to understand the primes and then build it up from that. This is abstract nonsense that says you can look at what's called families of L functions. And there are certain types of L functions that behave like other L functions. So if you have L functions coming from elliptic curves, maybe they behave one way. If you have L functions coming from Dirichlet characters, maybe they behave one way. And you can collect them. And the next thing you can do is you can combine them and make new families of L functions. These are called compound families. And the hope is that you can try to understand a compound family in terms of its constituent parts. And so there's a lot of technical stuff going on here. What I basically discovered years ago with one of my co-authors is given a family of L functions, if things are nice, you can associate a symmetry constant. 0 if it's unitary symmetry, 1 if it's symplectic symmetry, minus 1 if it's orthogonal symmetry. And we have the following truly wonderful theorem. If you have two nice families of L functions, then the symmetry of the compound family is the product of the symmetries. So anything with a unitary will become 0. Anything with a symplectic is unchanged. If you have two orthogonals, it can actually become a symplectic. So again, the actual details don't really matter here. But there is a way of combining families of L functions to form a new family of L functions, and we understand the behavior of its zeros in terms of the behavior of the constituent parts. Interestingly, we don't really have anything like this on the random matrix theory side. So the question becomes, random matrix theory does such a good job modeling L functions, and this is the project I'm really excited to work on. Some students from this past summer have already started looking at this. Can we combine families of matrices in such a way as to mimic this convolution here? Or if not, can we at least find interesting ways to combine families of matrices and see something interesting? And what we've been doing so far, so we're calling this the disco of two matrices. So you have families of matrices A and B. The disco of A and B is the matrix ABBA. Anybody figure out why we call it the disco? Any thoughts? Yeah, it's ABBA. So earlier today I was talking about ABBA and the great music group of the 70s. So we have left that in the paper for now. And then the question is, what can you say about the distribution of eigenvalues here? And we are seeing some things that are very similar to what we were seeing for convolutions of families of L functions. And so the question is, if A and B have certain properties, what can you say about the distribution of eigenvalues in this case? And it all comes down to understanding moments, and because this is a block matrix, there's a lot of stuff that can be done. So this is a project that is very amenable to analysis. The last thing I want to do before we have our first break so there's something called cuspidal new forms. We talked about the Riemann zeta function. We talked about L functions associated to elliptic curves. There's something more general involving cusp forms. So this project does have a little bit of reading that you need to do. Let's just say that there's such a thing, they exist, and they have properties. We have some kind of averaging formula, similar to the way in random matrix theory we had to integrate the polynomials in the matrix elements. We actually have ways to calculate stuff like this. We already have an explicit formula that relates the zeros to things related to this, and we actually have tools that allow us to handle this. The tools are not as good as the stuff in random matrix theory, but it's at least something. And we want to calculate our test function. These are the zeros. This is some kind of rescaling. We want to calculate a quantity like this. And there's lots of sums that arise that you need to do. And I'm going to skip a lot of this stuff. And then you're skipping all this stuff, skipping. And here's the interesting thing. So the one-dimensional case was done by Vanya Tluosanek. So two of them were my thesis advisor. One of them was a postdoc of one of my thesis advisors after having been the graduate student of my other thesis advisor. And so the one-dimensional case was done, so I wanted to do the two in the higher dimensional case. And we had a double integral like this to do. If you know what a Bessel function is, we've got a Bessel function floating in, which is not pleasant to deal with. And what I noticed is if you do a change of variables like this, you can convert this to essentially a one-dimensional integral with a new test function. So I can at least go through the conversion factor. So let's let u2 be x1, x2, u1 be x1. We can express the x's in terms of u's. I'm sure you all love and remember the change of variable formula for multivariable calculus and calculating the Jacobian. We get to calculate the Jacobian. We substitute that in here, and we get the following expression. We get the log of u1 and then the log of u2 over u1. Well, the log of a quotient is the difference of the logs. So when we put that in here, one of the terms looks like this. And this is essentially going to just be, if you've done any probability, this is essentially a convolution. And so this will give us a new test function evaluated at the log of u2 over the log of r, and when we feed it back in, it now looks like the one-dimensional integral with a different test function. And so, I realize this is a high-level blitzkrieg. What's going on is there's no such thing as a free lunch. We had a very painful integral, and by doing this change of variables, we bypass that integral and we get this new expression here. And at the end of the day, this is a much easier integral to work with, and we have the answer. But we want to show that this agrees with the random matrix theory predictions. The problem is random matrix theory was expecting us to slosh through this integral. And so things look different. So we then have to do some bookkeeping at the end to show that the two things are the same. And then there was a fascinating thesis a couple of years ago at Michigan by Peng Gao, who was a student of Soundararajan and Montgomery, the same Montgomery from before, where he was looking at families of Dirichlet L functions, and he calculated the low-lying zeros, the n-level densities, and he was able to calculate the answer for larger classes of test functions than anyone before him. And he was able to show if n was less than or equal to 3, the random matrix theory prediction and the number theory prediction agreed, but once n was 4, he had the answer computed in both cases, but he couldn't show that they were the same. Combinatorially, he just couldn't do it. So one of my thesis students at Williams was able to prove initially only up to 4, but then eventually he was able to prove in general that they are the same. In fact, let me just punch up his thesis. Should not take long. It is the best opening to a thesis I've ever seen. So this is the 4-level case. All right, so this is the quantity he needs to look at. And he needs to show that that equals the following. All right, just to make sure, did everybody have enough time to look at this? So he expands things out. Okay, that sounds not so bad. And homage to Spaceballs. The point that this is making, and I hope it's making it well, is that you need a way to look at things. How do you collect terms? How do you do the analysis? It turns out that this change of variables we did, it is hard to show that it agrees with the original determinant expansion, but the new formula is more tractable for a lot of calculations. And so we've actually done some calculations with this in various settings. And we are close to being able to prove we can do things for a larger class of test functions than people have done before. There's one or two mistakes that still need to be cleaned up. And then what Ivan Yitzdo and Sanak did in their original paper is they had some conjectures on behavior. And if these conjectures are true, they can get even larger classes of functions to work. It's not clear what the generalization of that conjecture should be to higher dimensions. So these are some problems that can be worked on. These are at a much higher level. There is a lot of number theory prerequisites. If you want to go this route, you are welcome to do so. It is going to require a decent amount of reading to be at the point where you can understand things well enough to be able to do the calculations. It doesn't mean that you would need to understand all of the reading. And so again, once I pause and start letting this upload, I'll talk a little bit more, but I want to just give you some sense of the random matrix theory. You can look at either a specific ensemble of matrices and try to calculate the density of states, or you can try to look at this new disco process, which we've just started looking at, and is having some very interesting behavior. For the L functions, there's a lot of stuff we're doing on the distribution of low-lying zeros. And the question is, can we push any of these results further? So before I hit pause, we take a break. Any questions on the avalanche of material that has come? All right, so I'm going to hit stop.